Ladies and gentlemen, may I have your attention, please? Please silence your electronic devices at this time. If you have a question for our guest speakers, you may send a text or email to askmetncyber@gmail.com. That's askmetncyber@gmail.com. And now, please welcome Brigadier General Paul Fredenberg, United States Army retired, Executive Vice President, Defense and National Security, AFCEA International, who will introduce our speakers.
And I'm glad. I'm glad that you all are here participating in this panel. If there's anybody out there on the floor that wants to learn about quantum computing, please come on in and join us here. We're going to have a very good conversation, and you don't need to be a physicist to listen in, because I think we're going to break it down Barney style for everybody here today. So I think this will be well worth your time to participate. But welcome to our micro keynote pairing on quantum computing. We're going to have presentations today from Mr. Bill Newhouse, who's a cybersecurity engineer and project lead at the National Cybersecurity Center of Excellence, and Mr. Jim Matney, Vice President of Strategy in GDIT's Defense Division. So to maximize everybody's time today, we have a very short time. This is going to be a lightning round, but their bios are both in our website, and they're available from the conference app if you want to learn a little bit more about their background. But I can assure you that they are both have all the credentials necessary to have this important conversation. But without further ado, please welcome, gentlemen. Thank you for being here today, and looking forward to what we have to say.
Thank you, sir. Thank you. You want to go first? All right, please.
All right. Hey, I'm Bill Newhouse, and I work at an applied cybersecurity center that belongs to NIST, so I'm a NIST engineer. And at the center, we try to demonstrate that standards and best practices can be implemented in today's technology. And those kind of projects, standards tend to lag cutting edge. This project that I'm leading is called Migration to Post-Quantum Cryptography, and it is complementary to my colleagues at NIST who are working the process, the quasi-competition, to select quantum-resistant algorithms. So post-quantum cryptography is trying to find new algorithms that can be run in today's technologies, today's hardware, in regular computing devices, not anything quantum. These are algorithms that are running on traditional classic computing, and they will help us to protect against a cryptographically relevant quantum computer. So we'll be going back and forth in questions and comments and talking about it, but this task of migration is necessary because all cryptographic migrations take time. There are algorithms that NIST has deprecated in the last decade that are still in use today, and lots of organizations may not even be aware of that based on what they know about their own use of cryptographic technologies. And so our project is going to talk about discovery. Our project is also going to talk about implementing these new algorithms that have been selected so far only in draft in today's protocols that we rely on. So I think from that perspective, I'll be able to talk to you about what NIST is doing in that selection process for the algorithms themselves, and our important work just to get people taking the necessary first steps. And I'll stop there and let Jim describe his interest in the space, and then we'll go back and forth.
All right, very good. Thanks, Bill. All right, first off, who attended the, is my mic on?
It's on.
Who attended the session yesterday on quantum computing? Right, with the panel of experts? Well, besides, we had the Talus that was there, but the one that actually, the quantum computing piece that was there on the panel, right? I thought the panel, the experts did a great job at describing quantum computing. I mean, they mentioned everything from superpositioning to the entanglement to the block sphere to just the fact that quantum computers are a lot faster than classical computers, right? But what I want to do is just break it down to as the why. Why is that? So quantum computers aren't necessarily just the next generation of a classical computer. It's different. It's completely different in the way that it computes and actually stores information. Now, my very good friend and mentor, Garrett Yee, how many people know Garrett Yee? Everybody from distance should know him. Told me, Jim, quantum is kind of a complex subject, so you need props. So I came up with two props right here, right? right here. So you see I have 53 qubits in this hand, and I have 53 bits in this hand. That represents a classical computer, right? So I got 53 bits. Now why did I pick 53? Well, in 2019, Google claimed quantum supremacy. Quantum supremacy is when you're able to build a quantum computer that actually can compute something that a classical computer can't. And they were successful at solving a problem in 200 seconds that would have taken the world's fastest supercomputer 10,000 years to compute, right? That was with 53 qubits. So when we talk about the number of qubits that each of the different companies are creating, we need to keep that in perspective. So, quiz. You have 53 bits. How much RAM, how much storage potentially can 53 bits store? Anybody? How many bits make a byte? Right? How many? 8. 8 bits makes a byte. So 1 byte is 1 character, right? Which means 53 bits can potentially just store 7 characters, okay? Now, qubits, everybody heard about superposition, right? That means a qubit can essentially be a 0, 1, or both at the same time. It can store 2 bits of information at the exact same time. Okay, so that's 2 to the nth. Nth is the number of qubits. So when you think about, like, how can that happen? Just think of it like this. And they talk about a block sphere. It's a 3-dimensional sphere, whereas normal computers has 0 or 1. It's just a plane, right? So if you look at it 3-dimensional, and you think about it this way, I'm looking this direction here. There's a probability that I'm looking left, but there's also a probability at the same time I'm looking right, correct? Right? Those are 2 different states that exactly are on the single vector, right? So you can have it. So that's where when you look at a qubit, it can store 2 things at the exact same time. So it's not an either or like with the classical computer. So who can guess how much information can you store in 53 qubits? Anybody? Throw out a number. How much RAM? How much storage? The answer is 9.0 to e to the 15 is the number of bits, the equivalent number of bits that they can store. And if you're not familiar with e to the 15, you move the decimal point out 15 spaces. Right? It's a very large number. It also equates to 1 petabyte of information in just 53 qubits. So when you look at that and you take that into context, so as we look at these different computers, you heard IBM just released there. They have 433 qubits, right? You look at the, the IonQ, right? They have a 64 qubit computer or a 32 qubit computer. But it's because the qubits are different. And you heard that from the panel, if you're on or listening to the experts yesterday to describe, there's different means of having qubits, which today it's all transistors in a classical computer. But because there's different means, you've got trapped ions like Honeywell and IonQ are using. You've got from IBM and Google, they're using superconductive material that has to be at near absolute 0, which is why it can create, it's a very challenge to be able to create the qubits as they described yesterday on the panel. So those number of qubits, when you look at it, everything is based on like being able to fix the error rate. So everything they said on the panel yesterday I thought it was outstanding. It was a very good lesson. But what I'm trying to do is bring it in as to the why. The why is an important issue that we have today. And as Bill mentioned, with the efforts that they're doing in building out quantum resistant cryptography, is because it is a threat to cybersecurity. We are making advances. I picked 53 because at the same time that Google did 53 qubits to solve that problem in 200 seconds, IBM also had a 53 qubit computer, quantum computer. And just this year they released their 433. So if you're on a track of doubling every year, they're on it. They're exceeding that track of doubling the number of qubits that they're having. So the advances in that piece and the timelines that you heard yesterday and everybody's been talking about and what you read is about 10 years. Forrester just released a cybersecurity report last month that claims that you need 1,000 clean qubits, which means doesn't have any errors, in order to be able to solve or have an impact potentially against cybersecurity. But that equates to about 1 million to 10 million regular qubits, right? Just because there's so many errors, as it's 2 to the nth for the increase in amount of storage that you get, it's also exponential in how many errors you get if you have qubits that are actually producing a lot of errors. But the reason why there's difference is because of different types of qubits. So you have photons and you have trapped ions that are dealing with atoms. It's not superconductive material where every qubit is different, so it has a different tolerance to errors. So you have it to where these are clean qubits. So when you have an IonQ quantum computer that is programmable at 32 qubits, that could equate to someone else's quantum computer that might have 1,000 qubits, right? Because they have clean qubits because it's dealing with atoms. But the other piece in regard to that and the timing is all based on the ability to be able to leverage these quantum computers to crack our current encryption. Okay, so that's based off of Peter Shor. How many people have heard of Peter Shor's algorithm? Right, we got a couple hands. How many people have heard of Love Grover? Right, how many people have heard of Klaus Schnorr? Right, and then there's another one, Babai algorithm. There's multiple algorithms that are out there, and the thing is, the problem set is a different problem set, and that's where we at GDIT, we consider that as where it's essential. All of our timelines is based off of Peter Shor's algorithm and the need to get to 1 million, where he even states it takes 1 million qubits to be able to crack RSA 2048. And they estimate it'll be 10 years, 10 plus years to be able to get there. But what if the algorithms or the different algorithms are used to be able to shorten that time span? AZO Quantum, a online publishing group who actually keeps the latest of quantum, actually published something recently, just in January, which states that some researchers have combined the shortest vector problem algorithm of Klaus Schnorr plus Babai that reduced the number of clean qubits required to crack encryption or current encryption to less than 400. So the problem set is different. So as we look and we attack this problem, we have to be ready for it. So when we look at this, this isn't something that's like Y2K that says hard date in the sand that this is when the problem exists and we're approaching it. We have a moving target of people, very smart folks that's around the world that are looking at ways to reduce the error rates required as well as the methods they're using to do integer factorization. Because it's already proven it can be done. Now the problem set is, how do I make it more efficient? And there are a lot of smart folks that's working hard to figure that out. So as we approach this, what GDIT has done is we created a resilient, we call it resilient framework, post-quantum cryptography framework, which actually talks about building our understanding the risk and building a strategy around that risk, doing the assessment, which everybody's required to come up and do the assessment. But the approach we're taking on assessment isn't just give us a list of all your crypto. You got to, and the points that was made yesterday I thought were very good, where it says you got to understand what systems, what data. But it's not just being able to encrypt the data. You have to look at it across the IT services. Like your browser, is it equipped for what type of encryption can it support? So if you're viewing data off of your application that's there, what security or encryption is being used by the browser? If you're storing that data on your laptop, what data at rest encryption are you using? If that data is being transmitted from one building to another, normally you have a TAC lane or so, right? What encryption are you using to encrypt that data as it moves from one building to another? Those services is our approach of being able to come up with the assessment. So we're looking at it and working with organizations to be able to understand across understanding their actual mission critical systems and the data, but then how that data flows and what IT services it actually goes through. Then we look at the work that like NIST is doing, and we're a big fan, and we've been following NIST for many years now, and actually been building out in our lab and demoing the capabilities, like the Crystal's Kyber, which they selected. Leveraging those, because that actually solves the PKI issue. But what if there's algorithms out there that can impact the symmetric? Nobody's talked about symmetric. But in the future quantum and the advances that comes with quantum, what if that happens? So our framework's designed to understand that this risk may change, but then also, as we go through the piece of building out and prioritizing and developing that roadmap plan for being able to implement the ones that is necessary. If you have encryption that's going from building to building and it traverses underground, that may be a lower threat than something that is leveraging commercial comms to actually go from this base to another base. So that's why it's important to build out a plan and a roadmap of the prioritization, And you heard this week, in a year, we're required, or organizations are required to come up with how much it costs to be able to, so they can start budgeting and planning for this. But that's where what we've done with this framework is to build this piece out. And the last phase of our approach, we have it to where we build the goals and the strategy, you assess, you migrate, and then last is the monitoring. Because this isn't a one and done type situation. This is something that'll have to be continuously monitored to make sure we understand the threat as quantum advances, but then also making sure that the solution sets, if there's new standards that gets published, that we're implementing those to make sure that we stay secure across the enterprise. And I'll leave it there for questions.
Cool. How many people here in the room think their job jar says, I need to worry about migrating to post-quantum cryptography? You're in that swim lane already. Raise your hand if you think you've been given that responsibility at your organization or company. Okay. And then the secondary question, does that mean you need to implement it in the technologies you sell and the services you offer? Or, well, I can't frame that so you can raise your hand in a good way. What I'm getting at is we're focused here on public key encryption, asymmetric encryption, and I'm not a cryptographer. But I've learned, as I've paid attention over the years, that the math that underpins discrete logarithms and factors and primes is something that classical computing theorists recognized classical computing would take too long. By the time they could solve these problems and figure out the answers and break the keys, the time you needed to protect the data had already happened. So 50 years, 100 years, whatever they would put in those estimates. So that made sense, right? And now the potential for a cryptographically relevant quantum computer has been theorized. Mathematicians, the people who understand these technologies. At RSA, I heard a physicist give a good analogy. If you needed to make a sphere, design a sphere, and somebody gave you a pile of Lego, you could make something that looks like a sphere with Lego, but when you held it in your hand, it would kind of feel rough on the edges and all that. But if you needed to do something where you really need to understand it at a more granular level, the curves and everything in a molecule, a quantum computer would support that because of all the qubits and the ability to really refine and that's where I'm going to fail. I don't know quantum physics. But now somebody has spent all this time saying what quantum computers can do and theorems and Shor's algorithm and things like that. What that person started to figure out was they were trying to do some new stuff, lattice-based math in a quantum computer, and realized that it never got to work at a certain level. And so if you take the lattices to a certain size and a certain arrangement, which I can't explain, they believe that's going to protect us. So those are among the algorithms that have been selected for digital signatures and for key exchange mechanisms that NIST has already put out as a third round draft of keep playing with these, keep learning about these. This summer, NIST is going to put those out in a FIPS document, Federal Information Processing Systems document, that says we're aiming to make these the standard. As a draft this summer, you get to push on them, complain about them, argue with them, talk about key sizes. All the things it will take to implement those start to become part of the conversation for what they put in the final that would come out in 2024. At that point, the non-national security part of the federal government and the national security part of government will start working on how they will validate these cryptographic modules so that you can put them in technologies that you can buy if you're in procurement, okay? So we're at least 2 years, and it's going to take a little bit of time after that, from being able to purchase this stuff, let's say. So what are you going to worry about now? And I mentioned earlier discovery, and I mentioned earlier playing around with the protocols that Jim was just talking about. TLS is already undergoing a transition to TLS 1.3. Some of the choices made there make it less obvious what the negotiations are doing and understanding what exactly got negotiated as you set up that session. That's complicated stuff. I'll back away from that in a moment, but there are also IETF, which is an international standards organization working on X.509, which is a protocol we rely on to try to figure out, we have these 4 things we can play with, how would they fit into X.509? How do we implement it? And so at the center where I work, we've signed CRADAs, Cooperative Research and Development Agreements, with 19 different companies. Thales in the room is one of them. Probably a few of you work for other companies, and I don't recognize all the faces because we've only been on Zoom mostly, but Gina here was on the panel yesterday. And what we're doing together is, if they have discovery technology, we're bringing it into our lab, and we will publish this summer late summer, what we've learned from those tools. And what that means is, where do I need to discover? How do these tools help me discover in those places? Network traffic is a good place to go look for crypto. So those tools exist. If you have applications and operating systems that go and they reach into certificate stores and do other things, we want to know all those conversations. Some of those will be tracked in the network traffic, but there'll be hard-coded decisions that in the software. Wouldn't it be nice to know that we're relying on an app that is relying on a potentially vulnerable algorithm? Then later you can decide with a risk tool that that app is supporting nothing important. It is supporting reservations for the golf course, not a thing I need to update or modernize. But if it's closer to something you design as it's deemed to be a high-value asset, you'll need to make some decisions there. So I mentioned code discovery. The ability to look into the applications and the software you're running starts to sound more important. And we've been saying this for years. Static and dynamic analysis of code would really help us, and doing better code overall would help our cybersecurity posture writ large. So in the two efforts we're doing, we're trying to get people just to understand there are tools. We're not telling you which tools. And we're trying to help you understand that the protocols where these asymmetric algorithms are currently being used, which is establishing keys by using public and private keys, these are the places that need some attention. And the good news is the people you rely on, if you're buying cloud services, if you're using Microsoft Windows and other technologies, if you're using AWS, if you have hardware security modules from different companies, they are participating so that they can tell us what they've already learned because they're doing the work themselves, but they're also communicating across this consortium. So the good news is, if it's in your job jar, you're gonna be inviting these vendors in to tell you how they do discovery. You're gonna be inviting them in to tell you if they're the ones who force you to negotiate the TLS, how they're updating those ends of your devices communications. And that means you can probably not rush into this. And NIST will be working on the validation stuff, and none of the old algorithms will be deprecated right away. Maybe on the day that we know a cryptographically relevant quantum computer exists, NIST would say, stop. We need you to stop using those algorithms. But until we have a little more evidence in that space, it's going to be a measured approach. And at RSA and a lot of the vendors, the word hybrid starts to pop up. Run today's algorithms and the new algorithms, and that's going to be also a risk calculation that we're going to need to try to describe and focus on. So I just wanted to tee that up because we really want you guys to ask us a lot of questions. I'm sure there was like 10 other things that popped in my mind when you said some of what you said. But I hope that you guys will bring stuff to us and also your expertise for the other stuff here. Do we have microphones that they'll be able to use for questions? We'll make the Brigadier General run around. I'm kidding.
Yes, we do
with
have
the
a microphone,
yes. If that's possible. I'm sorry we didn't tee this up earlier. If not, we'll repeat your questions so everybody can hear it. Are you good with taking some questions?
Oh, definitely.
Cool. Go for it. He's coming. Hold on. We'll make you the extremely novice user of the microphone. Thank you.
So a novice question, because I'm not a computing guy. I'm in electromagnetics, something totally different, obviously. So I just dabble in this stuff. So apologies if this is not a good question. But you mentioned earlier in the talk that quantum computing is not going to replace conventional computing. Rather, it has different traits that it is good at, that make it good at certain things and not so good at other things. Right. So my question is this. As we watch quantum computing progress and get to the point where it can start to attack our cryptographic algorithms, what work is being done to look at new means of cryptography that leverage the strengths of conventional computing and are particularly difficult for quantum computing, and maybe doing a layered approach, similar to what you said on the hybrid? Over.
Yeah, I'm sure I won't cover the full breadth of that question. One of the things that is happening, and some of the booths may be part of this conversation, is if you say asymmetric and public key encryption is not, it will be exploited by cryptographically relevant quantum computers, are there other ways to protect your data, your high-value assets? And the answer is yes and. Yes, people are talking about quantum key distribution, which would be establishing sort of an out-of-band network to move your keys around. I worked at NSA early in my career, and we had KG84s and KG81s, which were symmetric encryptors, and we had a system by which keys were delivered to this site and that site, and that was except for that guy Walker, really a good system. And symmetric encryption, we didn't worry about it too much being broken because the key was distributing those keys. Public key started to enable encryption's use writ large, obviously, and that led to changes in what kind of cryptography the US government allowed and uses. So I'm mostly just talking, I said quantum key distribution. Move the keys around in a system that you believe would be not vulnerable. We need more eyes on those systems to understand, does that introduce other new vulnerabilities? Same thing is true of these new algorithms. We need a lot of eyes, and the reason NIST is doing it as an open, transparent process is so that people can and will hopefully see that every flaw is available to be found by anybody, and not because it was engineered in or anything like that. So that's my simple answer.
And, to piggyback on the success that NIST has been having for years now, they've been doing a competition, if you will, for rolling down select for what is the viable quantum resistant or quantum safe type algorithms that they will be able to select as the standard. So a lot of effort that they've been doing in being able to do it. They just finished just last year, released the fourth round of those actual algorithms that are quantum resistant against. So when those are put in place, they'll be the ones that be resistant to any type of quantum attacks. So, and where I'd reference, our approach, the resilient approach is what we called it is about the implementation of the approved standard. So when NIST comes out and says, yes, this is the standard, okay, so what areas within your architecture does it affect, and then how do we go about implementing it? So yes, there's work being done to select it, but then the focus and, the number one issue really is about the implementation of it. How do we implement it in a short amount of time that doesn't take as long as like SHA, which took like 15 years to implement, right? You don't have that much time. So we need to have a methodical approach, a very deterministic approach to, okay, this is how we're going to implement new standards as they're actually produced to be able to mitigate this threat that we know is coming.
Does that help? Cool. Anybody else with a question? Please.
Come on, make it hard. Otherwise, I'm going to ask you how many qubits are in 100.
I'll bore you with something. The White House put out a memo, first NSM 10, that said do many things quantum. Let's get the quantum advantage for our nation, and that's wonderful. And it has some things that we're doing, which include selecting these algorithms. Cool. We'll take the question over here. The other thing is that in the fall, M2302 came out, and as of today, the 4th. Yeah, today, every agency in the non-national security part of government has to identify their high-value assets and fill out a spreadsheet to say something about the crypto that surrounds them. That's a useful thing if your job is to protect your data. That's a useful thing if you're approaching doing zero-trust architectures. So what I try to communicate is there's value to do this because you also already care about continuous monitoring. You already care about endpoint detection and response because that's where your data could be exploited. So it's part of an overall journey. You're not the lone solo person doing high-value assets. I think the mic's over here. Yep. Go for it.
How do we better protect the research from near-peer competitors that are also interested in quantum supremacy?
So protect from near-peer, it's basically making sure you're running algorithms that have been tested and proven. And in this case, yeah, if you call that a high-value asset, so don't let the research end up in the wrong places is part of it. I'm no expert in all the exploitations of the DIB and any place else in the commercial sector, but those are your high-value assets, and so therefore somebody should be focused on what's hidden that we haven't talked about is right now organizations could be collecting traffic that has got your data in it so that when there is a cryptographically relevant quantum computer, they could use it to break the keys, go back and exploit that traffic. That's pretty complicated, but if you think you're running the kind of lab that has a high-value asset, you should be telling your folks that we need to be in this space of migrating as quickly as possible.
And you're able to have that architecture build out laid out, so then as the risk is changing, or the threat changes, where the timeline is moved up, we know and you prioritize and you have your implementation plan to be able to take these standards that we know is there and then be able to apply those. Because it's not going to be something that's cheap. Potentially it'll be something that's very expensive. But
yes, over the summer, NIST announced algorithms for key management as well as
Digital signatures.
Digital signatures, yes. Mm-hmm. Thanks for that.
No worries.
So my question is, how do you envision the rollout happening? And then secondly, do you envision both traditional algorithms as well as these post-quantum operating in a hybrid mode? 'Cause
Yeah.
I'm trying to track, there aren't any standards for those, or do you think that over time, these algorithms will be secure enough that we wouldn't need the classical algorithms, and over time everything would just be, post-quantum, and their variants? So just kind of want to get your thoughts as to what the transition would look like.
Yeah, so the vendors have been reading the first 4 selection choices, reading through it all, and contributing. There's a forum that continues arguments about it. NIST at the same time said, we have those 3 digital signatures and the 1 CHEM, key exchange mechanism. We need more. We want to diversify. We don't want to be all lattice-based. So that's a continue the standards to identify potential future algorithms is happening. Hybrid, I think based on the way the industry is talking about it, it's going to be, and the practicality of it is going to be the answer. Now, what does NIST need to define so you don't do hybrid badly, and then test to show that? That's more details than I have in my head, but that'll be amongst the documentation that we're exploring. It's going to be complicated because if we can't see in there and nobody else can, then that's hard to say that's a good implementation. And so saying that an algorithm has been produced properly is done through a testing process where we've accredited labs that aren't part of the government are able to do that, and then you get FIPS 140-2 compliance. That will need to be updated to support the new algorithms and hybrid as that language gets codified as being, let's get the language around hybrid clearer so that you know what you're getting. It's a little bit like walking into a car dealership. If it says smart brakes and then they say safety sense, which one says I can't crack into the wall? It's the second one, but if the sticker just said smart brakes, you're like, I could probably not hit a wall by just the car will stop automatically. We need to make it so clear and obvious that it's not automagic, and it might be in the same space as SBOM, which is software bill of materials, cryptographic bill of materials. So as you go to buy hardware, you at least have an understanding of what they're offering. That still doesn't remove the complexity of looking deeper into it. So it's a lot of work to get there, which is why start now so we can have some failures in exploration and research, and then success in implementations. So.
Yeah, next question.
That was our final question. We have run out of time.
No.
Please welcome.
No, we get more because we started late and we were supposed to go to 11:45.
Oh,
Please.
by all means.
And look at the general. Look at his face.
See that?
Okay, well,
He's got that angry Brigadier General face going.
That's right.
Stop smiling, sir. Sorry.
I guess I'll have the closeout question.
No, you
then.
got more than time than that.
With AI and ML running at the speed it's running at now, and quantum becoming more available as we go along, how are those two going to converge, and what's that really going to look like, especially for the DoD?
I work for the Department of Commerce at NIST, so no comment. But AI has already been used to attack a side channel attack on crypto algorithms, and so it will offer some means to make that more. If that gets shared, that those dangerous things will be in front of more adversaries faster. Is what I worry about.
Right. And I agree. I mean, the way I see when it comes to quantum and quantum computing is I believe it'll make AI what it was envisioned to be. It'll make a lot of the different optimization type problem sets more of a reality. It'll be able to compute those. Will the classical computer still be able to have benefit and use, when it comes to quantum computers? Of course, and they'll still leverage, the AI, the MLs for building out your machine, the machine learning pieces to be able to compute and determine what the outcomes of future data may be. But when it comes to optimization type problems, that's where quantum computing will be able to have the leg up, if you will, when it comes to the comparison between the two.
We still have time for plenty more questions.
I got a question. So we're always thinking classical ways as we take on new things. Have you considered the possibilities of quantum as far as how do you take advantage of the duality of light or streaming across different packets, taking advantage of decoherence to send dummy packets across, using quantum computing to its full potential as a paradigm shift, and how do we secure it non-mathematically using all the different principles that quantum taught us that can throw off an attacker and keep them busy for years, if not decades, trying to crack it?
All right, I'll take that one. But no, that's good. I mean, we focused the conversation on the cybersecurity threat just because of this conference, but quantum computing, the potential benefits that quantum computing brings is just off the charts. I mean, from medicine, from improving, the efficiency of batteries. Everything's going to electric cars and everything, right? So it's improving just the chemical reactions on various things because it has the ability in a single operation because of this data. Remember 53 qubits, petabyte of data? So that's the amount of data that can actually, with 53 qubits, you can actually have to be able to run in a single operation, right? So whereas normal classical computers compute things in a linear fashion, if you wrote code, it's top down, right? You execute, and but it's running in a linear fashion. So it's with quantum, everything runs. It takes all those different variables. It can store all those variables at the same time and run all of those variables in a single operation, which is why those optimization problems. So when it comes to more targeted and focused medicines, when it comes to cyber, we can be able to leverage it to be able to identify the potential behavior patterns of potential insider threats or even hackers. So the ability to leverage quantum to enhance our ability to defend our data as well as our networks, I think will be enhanced through the use of quantum as well.
Chris Daly with ActiveCyber.net. When it comes to operational technology, how do you feel that the PQ candidate algorithms cover that? I mean, do you feel confident that the coverage model for both current and future operational technology is going to be supported by those candidates?
So one good bit of progress is NIST Special Web 800-208 and the CNSA 2.0 memo from NSA says implement state-based hash algorithms that if you're going to be doing firmware signing and things like that. And so in operational technology, you're putting, and true of IT as well, but you're putting devices in that you might not be able to take out for 20 years and things. So that's one space where you could right now start implementing a process where your firmware signatures are better protected. So small win there. The other algorithms I haven't studied, but my colleagues have, and that's one reason to keep asking for more potential algorithms because of the computing and memory and other space requirements in OT technologies. I've heard OT vendors talk about building their next gen stuff with room to grow into these algorithms. That's great news. That doesn't help you if you've got 10 years more with today's gen. So there's going to be other people offering you prophylactic solutions around those things potentially to give you some of that risk mitigation now. And then it kind of the protection, if asking yourself the high value asset is that it keeps running, that something keeps flowing and all that is a risk calculation that your OT experts, I hope, will keep pushing these algorithms to be the space and size constraints that they need. And it's not there yet, but some of the algorithms are a little more useful than others, but still that space is, lightweight cryptography is difficult and needs some more thinking in this space too. And if you have any answers, give us the websites and we'll do the research with you. You're allowed to, shill your own stuff here too. This is a community that should learn from each other. Shill's a good positive word. Share your good learnings.
And that's why the approach that we take is a risk-based approach. We look at it from the same way that you do from cyber, right? You assess, the threats. You come up, you build your course of action of what you're going to be able to do to that. You prioritize and you implement, and you continuously monitor. So we designed a construct to be able to support that way because things are going to change. The risk is going to change. I mean, right now, everything that we know that we've been hearing on the timeline is based off of Peter Shore, but I'm telling you, there's really smart folks out there, and there's already some other algorithms I mentioned previously that is looking at it from a different angle that can shorten that timeline. So it's that preparation. So as we, the approach for being able to identify where you use encryption, we have to think of it more than just your point-to-point circuits like the old KGs and everything that was being used, or TAC lanes that are in use today. Is look at it across all your different IT services and what encryption is being used for each. When you log in on your web to your bank and you see that little key up there, click on it. When you click on it, you'll see what encryption is being used, and you'll hear the same names that we've been mentioning that's been discussed during this week. So this is a threat that we have. It's not just to the DoD or across. This is something that can impact across the world in the way that we communicate and deal, across the internet. So the efforts that NIST is doing and all the researchers and coming up with quantum-resistant cryptography is great work. So now it comes to, okay, what are we going to do about it and how are we going to implement it? And that's where the focus is. And the whole capture now, harvest now, playback later is a real threat. I mean, we've done it for years, and being able to intercept traffic, decrypt the encryption, right, and then use it to our advantage. I mean, we've a lot of history associated with that. This is no different. So they're siphoning that data off now. So now now is the time for us to be able to treat it and say, okay, the threat is now because they're harvesting the data now, right? So the fact that they might not gain benefit from it might be in between 5 and 10 years. Well, okay, but they're harvesting it now. So we have to consider that. That's why that planning, and you see how long it takes to plan and implement or even get funding. So that effort of being able to start with that and having an approach, a model to say, okay, this is the approach and the strategy we're taking, I think is critical for us to be successful at implementing the standards that NIST and the team over there are going to be able to publish.
Probably it.
Thank you, gentlemen. Ladies and gentlemen, please welcome back General Fredenberg.
Thank you. Bill and Jim, I do have one question. Do you think, as a nation, there's some emerging studies coming out. This is a critical technology capability, right? And I think about this era of competition, right? Do you think we have the right incentives for our industry, our S&T community? And I mean, do you think as a nation we're, focused on this enough and have the right incentives and things like that to drive that community to get, faster, right? Because everything that I'm hearing you say is this is critical, right? We got a long way to go. It's not quite there yet, but the threat is now, and collect now, read back later. But is there anything we need to do in that space to help us push this along?
I think the driver of NSM-10 and M2302 at a federal, non-national security and national security level is a good push. ONCD has grown, and it's new in this administration. Good experts, good cross-agency collaboration, and so to me, that's the good push. How much to invest in new technology is still a question, but how much to invest in preparing yourself for that new technology is, I think it's been emphasized pretty well, but we do need to get in front of people so that they understand where they fit in that model. So it's a journey that we don't have a great visualization of, so that if I learn this, where do I take that to make the next thing better? So that's, I think, still the part where we need to get across in front of more and more people to say what we said today.
Right. I 100% agree. I mean, 2 years ago, quantum was like on somebody's chart that was in the outer strategic area, but wasn't mentioned, I believe, once. There's been 3 sessions. Talis did a great presentation. We had the expert panel just yesterday, and we're talking about it today. So the conversation is there. Plus, some of the questions, and in the PKI presentation and another presentation was regarding quantum and quantum resistance. So the attention and the understanding, and that's the aim, is why we're up here now, is to try to really get the information out to enhance the understanding. But there's a lot of focus that really needs to get into, okay, how can we start educating the younger folks on how to code, to leverage quantum computing, to start learning Q# and such. So the more we evangelize and get this out and the understanding of the threat, I believe we're there. I think what Talis is doing and being able to integrate quantum resistance into CSFC. So some of our capabilities. So some of these things in the initiative. So you see a lot of the folks and the vendors that's out there on the floor are invested in that as well. So I think we're on a good track. We just need to make sure that the attention and the focus and the understanding that this is a threat that's today, because like you mentioned, the harvest now, playback later. So we need to really build that construct and make a concerted effort to make sure we get there.
Got to move faster.
Got to move faster.
Well, thank you very much, both of you. I appreciate this open, candid, and very intimate conversation with this group of dedicated folks out here that is going to make it happen faster. But in lieu of a speaker gift, FCA is going to provide a donation to the Fisher House in honor of both of your names. And so we appreciate your time today. This does conclude, finally, our micro keynote session this morning. Next up, though, in the main conference, we'll have a final keynote from Michael Clark. He's the Cyber Command's Director of Cyber Acquisition and Technology, and I'm sure we're all going to be interested in that, but that'll be in Hall D in the main theater there. Thank you very much, and we'll see you over there shortly.
Bill?